In this appendix, I would like to explain surface integral of spheres. But before explaining surface integral of spheres, I'd like to explain the spherical coordinate. In the spherical coordinate, we express the positions of a point with r, theta, phi instead of x, y, z Cartesian coordinate. At first, I'd like to write an x, y, z coordinate. This is a Cartesian three-dimensional coordinate. Instead of x, y, z, sometimes we use position. These positions can be expressed x, y, z. R is the distance from the origin. The theta is the angle between the z-axis with the position vectors. Phi is the angle between a projection of the position vectors on the xy planes, and then that vectors has the angle with the x-axis phi. So from these equations, these figures, you can find, look at this triangle. You could find this is r sine theta. This is r cosine theta. This means this is r sine theta. Then you could consider the triangles. This triangle. Then this length becomes r sine theta sine phi. This length is r sine theta cosine phi. Can be expressed r sine theta cosine phi. Y equal r sine theta sine phi. Z equal r cosine theta. So if you know the r theta phi, so you could write in the positions with the x, y, z. Then we would like to find out the surface area of a spheres using the spherical coordinate. So we can draw the spheres x, y, z, and take a really small areas on the surface. So this is r, this is theta. So this means this part is a d theta. So if you consider these sections of the circle, this is the part of the circles with a radius of r. So this length becomes r d theta. And also we'd like to use phi. So this is phi. Also, if you write on the parallel, this gonna be phi. So this means this angle is gonna be d phi. Then again, you can consider different circle. So this part is a part of the circles with a radius of the r sine theta. Then this length is expressed r sine theta d phi. So you can pick up these areas. Yes. So this part is r d theta. this length is r sine theta d pi. Then areas. This small patch of the surface of a spheres is expressed the product of these two quantities. So this means r squares sine theta d theta d pi. This is small area. Then we'd like to integrate over the surface to find the s. So two independent variables is phi and thetas. We have to integrate over the phi and thetas. Phi is changing from the 0 to the pi, phi to pi. And for the thetas, so phi is changing from the 0 to 2 pi. So covering this region. And one circle is 2 pi. But in the case of the thetas, theta is changing from the 0 to the pi. Then the integrations over the phi's covered the one circles of the rotations of these regions is one rotations. So should be is 0 to the pi. And the small areas you can write that the thetas and the r squares sine thetas. So this is the small areas. Okay. Then we could perform the integrals. Integrals over the phi it becomes 2 pi. And r square is a constant, r squares. And the integral of the sine becomes minus cosine theta, because the derivative of the cosine becomes minus sine, 0 to the pi. If you substitute pi, this becomes a minus 1, minus 0. So it becomes 1. So it becomes 2. So this is equal to that. So if you substitute 2, it becomes 4 pi r squares. As we expected, surface area of a sphere becomes 4 pi r squares. Then once you discover the surface areas of a spheres, we could find the volumes. So we could consider a solid sphere is composed of the number of the thin shell. Okay, then we just only consider some of the shell. And the radius of this shell to the origin is r. Then as we explain, surface area is given by 4 pi r squares. If we consider the thickness of the shell is dr, a volume of a shell, spherical shell is given by 4 pi r squares dr, area times height. So we could find the volume of a shell. So to find the solid spheres, you should integrate 0 to the radius of solid spheres. So this means 0 to the r. 4 pi r squared dr comes from this. Here, small volume. If you sum up the small volumes over the whole solid spheres, this becomes 4 pi 1 over 3 r cube, 0 to the capital R. So this is 4 pi over 3 r cube. So this is the volume of a solid spheres. Then I'd like to explain surface integrals. So we'd like to sometimes find the surface integral of a vector quantity over a solid spheres. So this is solid spheres we'd like to consider. Then, as usual, we just draw the Cartesian coordinate x, y, z. Instead of Cartesian coordinate, as I explained, it's really convenient to use a spherical coordinate and take a really small areas. This small area is expressed ds. Magnitude of ds is given by r squares sine theta d theta d phi. This is the areas of this small region. So usually this is the magnitude of the surface areas. But if you want to consider the integrals over the surface areas of the vector quantities, we consider this surface area is expressed as a vectors. Vector has a direction. This is a vector quantity. ds, vectors. This is a vector quantity. Magnitude of the ds vectors is equal to ds. This ds is a magnitude. Then if you want to consider the integrals, surface integrals over the spherical surface over spheres, you should take an inner product with the surface vectors. So in this case, if you want to consider the surface integrals of the vector quantity of A, you should always take a scalar product. This angle is, for example, alpha. You can write the scalar product is A ds vectors inner product is magnitude of A times ds and cosine alphas. Cosine alpha is dependent on the positions, so you have to integrate of the considering the sum of these quantities over the surface of a spheres. This is a surface integral of a spheres.